Okay guys, welcome back. Now we are almost done. We have only 2 blocks to complete our stand code. The first one is going to be the model that we have to just fill this out. For the model, we have to just, first of all, to define our priors. If we do not specify any priors based on the things that we have learned before, essentially we are staying to, I should say, to the stand to just use the flat priors, which is going to be a weakly informative priors for our analysis. Now, also for the likelihood, we just, I'm just going to first of all just write the likelihood that we have, then we just move on to just talk about, I should say, to talk about the priors that we can assign for our model then. For the likelihood, we remember that we are talking about normalized whole brain volume. We said that the normalized whole brain volume, it's normally distributed by essentially a mu and also a sigma. We know that the sigma that we have, it's going to be the second argument in the normal. But however, for the mu, we are just going to take the thing which we just got and compute it on the top as the normalized whole brain volume bar. I shouldn't have written that on the top. I should have been written it here, normalized whole brain volume, and I just put the bar over here. And that essentially defines my likelihood of the model. I have just done the for loops in order to find the mean for the normalized whole brain volume. And you see that the mu, which I defined here, and also as a parameter, which is defined in the parameters block. That's essentially defines my likelihood, and the sigma, and that's the thing we can also define a prior for that, or we do not need to just define a prior for that, but however, for the prior, if I just want to just define it, I'm just going to define something for the distribution of the random, I should say, the intercepts, which I'm just going to define it as a normal, which is going to be centered by the mean equal to 0, and the sigma nu. However, this is going to be the prior for the sigma nu. You may wonder what is going to be the sigma nu. You can think of the sigma nu to be also defined as a flat priors, but at the same time, you can come here to define, for example, your sigma nu. In order to define one priors, not as a flat priors, you can talk as, for example, it can be a Cauchy distributed. For example, it can to be centered, and for example, the dispersion of the 1. And that's going to also define, for example, our priors for the sigma nu. And let's see what's, okay, everything is fine. Now we have defined our priors, and you see that the only priors that I haven't defined yet, it's going to be for the sigma, and for the sigma, it's assumed that the prior is going to be a flat prior. You can also, if you want, you can define, for example, the prior for the gamma, for example, for the sigma that we have, you can define a prior as the gamma. It depends on you which prior you may just define. It's going to be more appropriate. I'm just going to define a gamma with 2 parameters, let's say 2, and for example, 0.1. Let's define this one. And also it depends on, let's say, for example, the information that you have from essentially from the data which you have. Normally, I just use a flat priors because I just let the data to speak for itself. But at this stage, in order to show that how to define the priors for your model, that's how we just define it on a separate parts in the model, and we define the priors like that. Then essentially, we are done with the model block. We define our likelihoods, which essentially it takes the object which I defined it in the transforms parameters for the random intercepts and for the sigma. And the nu and the sigma nu, I defined my priors. Also, there is one block which is left, which is normally essentially is regarded as the memory of my model, which it generates the replications for my model. If I can just come to define an object as normalized whole brain volume, and I call that as a rep, and that's going to be essentially as for example, it's going to be the replicated, it becomes the replicated of the replicated normalized whole brain volume. And in order to do that, I just can define it as a vector or a real number. We can just define it as a real number, but we know that we have to define the length of that real number in front of the objects that we defined. Okay, and now it becomes the objects that we defined. The next thing which I'm just going to do, I'm just going to tell the stand how to compute the normalized whole brain volume, which is a replicated one. In order to do that, I'm just going to write the for loop. I'm just going to write, for example, for any number, I can just define it, for example, for I. I had defined I before. Let me define j. For j from 1 to all the observations which I have. I'm just going to just write the body of my for loop, and that's essentially, it becomes whatever I have in the likelihood, I'm just going to define it here, except for two differences. The first difference, the normalized whole brain volume, it's going to be represented by the replication, the objects which I defined it on the top, and that becomes equal to, we do not show that as a tilde in the generated quantities block, and instead of showing it as a normal, we just show that as a normal RNG. That's the only difference which we have with respect to, let's say, for example, the model block and the likelihood. And essentially, I'm just going to write normalized whole brain volume bar. This one, it takes the iterations j, which I defined, and also I have here, let's say, the sigma, which I defined it on the top. And that essentially defines my, essentially, the generated quantities block. Let me see what is the object here. The right-hand side should be the real. Dimension mismatch. They have okay, let's see what's the problem. And that's the problem here. I should have just given, I should say, the same argument for the j here, because I forgot to do that and I had a problem with the mismatching of the dimensions. Because whatever I have the iterations for, it should also take the arguments here on the right side. Then now you see that the dimensions on the left side of the equations in the for loop equal to the dimension on the right side. And now everything looks fine. I do not have any error message here. And it seems that the things which I was looking for to define my stand model is pretty fine, and I'd have to just save my file, and we just go back to the R that we have. Before we just run the model, there is one tiny thing which I have to do, is that the other thing that we have to do when we just go back to the R, we have to define, I should say, the group level as a factor, and that's the thing that we should not forget. That I'm just going to do that here. I'm just going to go to the data. I'm just going to just subtract the group variables. Then I'm just going to write here as a factor, and the same thing, data and group. And that's the thing which we have to do. I'm just going to execute the code, and that's the thing which we have to do before we just go on and move on to do essentially write the R stand model then. Okay, at this stage we are totally fine in order to just move on and just write and execute the stand for our model. I'm just going to do that on the next tutorial. I'm just going to finish this tutorial by finishing and recapping the fact that we were able to just write the whole model for the random intercepts of the Alzheimer disease projects that we have. When we come back at the next tutorial, we show how to just execute the model and interpret the results.